My name is Guillermo, and I am the sustainability lead at Altu Architects. And I'm going to talk you through how we design large-scale, low-energy buildings by combining both BIM and Passivhaus. PHPP is the energy modeling tool for Passivhaus. So why we use Passivhaus is because by focusing on energy, it's able to design very low energy buildings that achieve a great thermal comfort. Over the years, the standard was created in 1991. It's been proven that the performance gap between what is designed and what is actually built, it's virtually non-existent. This also translates into buildings that are very comfortable for the occupants. That's achieved by having stable temperature throughout the year in winter and summer conditions. And that also results into reduced operational energy during the lifetime of the building and less CO2 emissions. We achieve that by using the energy modeling tool, which is the PHPP, which is basically a big complex Excel spreadsheet in which we input all the relevant parameters of the building, and that way we're also able to dimension to know if we need to add more insulation or improve a certain element. But the thing is that there is no direct way to transfer the data from our BIM model, where we've got all of our design information, into the PHPP, which is our energy design tool. So we have developed a workaround to do that transfer of information. So I'm going to just show you the actual process of how we do it. So let's see if the video plays. Fingers crossed. Oh, it does. Wonderful. So, so that's our BIM model. That's where most of our design information is contained. We've got our architectural GAs. We've got all the coordination with the structural engineers, mechanical engineers. We've got our build-ups, every single layer in our building, what material is going to be, the conductivity of it. We define things that are also relevant for Passivhaus, like the air tightness line, where we need to exclude or include certain elements, like, for example, cold spaces, like bike stores or bin stores, are outside of the heated space. In our BIM model, we also have construction information, so our sections will include all of our build-ups. We will also have everything related to window schedules, all the components that go into the building, which of course are very relevant because they will have different frame types, different types of glazing, and we need to incorporate all of that into our energy modeling. However, not everything that is in our BIM model is relevant for energy modeling, so we need to do specific model for Passivhaus. So for that, we first do several auxiliary calculations, things like measuring the treated floor area, which is specific for Passivhaus. That's basically the usable heated space within our building. And we're able to do that inside of BIM, so it's a fairly automatic process. Those are the plans measuring the usable space for Passivhaus. We also do like other calculations inside of BIM, like the volume of our building, which is relevant for our air test. Maybe you know that Passivhaus buildings need to be like very airtight, so we don't lose heat through infiltration. And then there are other calculations that we need to do on the side, like electricity consumption of certain appliances or water pumps, lifts. But then I'm gonna show you the actual tool that we use to translate the information from BIM into PHPP. It's DesignPH. It's basically a plugin in SketchUp where we create this sort of much more simpler model. It's like a cardboard model which only has the thermal envelope, so the surfaces in contact with the outdoor air, but nothing inside. So we've reduced the amount of information from the BIM model, and we create in it each assembly and component that we've got in our facades, roofs, roofs, floors. And we assign to each of those surfaces the type of assembly that is going to be. So, for example, that wall will be a brick wall with cavity insulation, but it could be a render wall, and we're just assigning that with a specific U value linked to that. Same with the windows. Windows will have different types of glazing, so windows on south or west elevations will have low G value glazing to limit solar gains. We'll be assigning all of that in this model here. And then finally, we will create the context of the building that is going to affect the shading and the solar gains that go into our building. And all of that is now possible to be transferred into a language that our Passivhaus tool understands, which is just figures, basically. We also need to look at thermal bridges. The thing with thermal bridges is that they're more difficult to identify in an automatic way. We first need to identify it, so identify the junctions where there is like a weak spot in our thermal envelope. Then we need to measure them. So in that model, we measure the length of each single thermal bridge that we've got in our building. So, for example, the parapet where they interrupt the insulation joining the roof and the wall, for example, or how the partition walls on the floor over unheated spaces interrupt the floor insulation as well. So all of that is incorporated in the building in order for the energy model to be as close to reality as possible. So what we actually do in BIM is we've got all of our details and we link that to the report in which we calculate the thermal bridges. That's done externally in another program called Trisco, in which every material has conductivity associated to it, and then the junction is calculated and you can see how the heat escapes through it, and we get two important figures from that. The psi value, which is the heat loss, and the FRSI, which is the condensation potential, which is also relevant for building regulations, as you might know. All of these to get the design information into our energy modeling tool. This is the PHPP. So it's just basically a spreadsheet. And we've got like three important parameters that we need to achieve: heating demand, overheating, and primary energy. Those are our main objectives or targets that we are trying to reach for Passivhaus. So for that, we've got all the information of our assemblies, so the U values of each of our thermal envelope components, all of the areas. So you can see all of this information is coming automatically from our SketchUp model. We haven't had to input that individually, which would, for these scale of buildings would be basically impossible. But it's all in here, along with the thermal bridges, and now we are able to tell how much heat is escaping through each of these elements. So how much heat is escaping through the windows or through the thermal bridges, what's the U value of all the thermal envelope, combining both walls and windows and everything. And that's helping us to dimension that. So if we need to upgrade any of those elements, we can do it, we can tweak it. The same with windows and doors. We are inputting every single kind of window and door in the building with the thermal bridges as well, associated with their installation as well. That all goes into our Windows tab. So all of the 565 windows and doors in this building are captured. Close. And I'm about to finish. Then we've got ventilation as well, which actually this one needs to be input separately. All of these to calculate the conditions for in winter. Then in blue we've got the tabs for summer conditions, because overheating is also important in Passivhaus. We try to limit that. And Passivhaus also looks at final energy consumption, so what the building is going to use overall. So what we achieve in the end is an energy calculation which shows in an energy balance graphic like this one how the building is losing heat and how we're compensating that with the gains. And only a small part of those gains that we need to compensate that heat that we're losing comes from heating. The rest comes from solar gains and internal gains, so the users, appliances, and everything. And the purpose of these things we're doing is that our actual buildings perform and use energy in a way as close as possible to what we have designed. So we close that performance gap. And those two buildings in the picture actually just became Passivhaus certified this week, which hopefully means that they will use less energy and be very comfortable for the users who start living in it. And that's it from me.